Alright, so we're going to talk about pairs of angles. Okay? How many objects are we talking about when we say the word pair?
Two.
Two. Okay? So what do I call a pair of pants?
One.
Why do they call it a pair of pants?
Just two legs.
So why don't they call it a pair of shirts? They got two arms, two sleeves, right?
Because you only have one torso that the shirt goes on.
Okay. Alright. That makes sense. Mathematically, when we say the word pair, we're thinking two. Okay? We need to first talk about adjacent angles. And this is something we've already defined previously. Okay? And adjacent angles are two angles that share the same vertex. Okay? Share a common side. Share the same vertex, share a common side, and have no interior points in common, right? Okay. Talked about this last week, but they are points, angles that are kind of positioned like those down there on the bottom. Okay. Angle 1 and angle 2, those are adjacent. They share a vertex, they share a common ray. And if I ever pick out a point inside angle 1, I know for certain it did not also come from angle 2. Okay. Same thing with the blue angles over there, 3 and 4. The issue arises in regards to adjacency if we have more than two angles kind of being displayed. So this is really when the issue occurs. Find some markers that work. There we go. Now these two angles here would be adjacent. These two are adjacent. Those two are not adjacent. Okay? And then if I look at that angle there, again try to find some markers that work. If I look at that angle and I look at that angle, okay, they as well are not adjacent, because if I pick a point out of this region, say that point right there, well, that point came from the inside of the red angle, but it also came from the inside of the purple angle, right? So that would mean that that point is a common point between the red and the purple angle, violating the idea of being adjacent. Does that make sense? Okay. So really, the only time that we really need to worry about common points is when you have, three angles right next to each other, like that picture, or 4 or 5, and you start talking about adding basically 2 of those or 3 of those angles together, and there's some overlap. Okay. But if we look at the smartboard, angle 1 and angle 2, they're adjacent. Angle 3 and angle 4 are also adjacent. Okay. Remember, adjacent means next to, but mathematically that's not a good enough definition. So we have to specify what does it mean to be next to. Okay. If I just say next to, that's kind of a gray area. I could say down here, these two angles are next to each other because they're pretty close to each other, but they would not be adjacent in the way we want to talk about it. Does that make sense? Okay. So we need to have a better definition than that. Okay. And that's what happens with a lot of the definitions we come across. They might not be all that awesome to remember and insightful in regards to a picture. This is an example of that. This definition is, I think, terrible in regards to how we can visualize what vertical angles are, but it does a great job of eliminating anything else by accidentally getting classified as vertical. Does that make sense? If we talk about, I think at the beginning here we talked about how we don't want a giraffe to be identified accidentally as a zebra or vice versa, right? Okay. So we make really good definitions for what a giraffe is, and that never happens. Same thing here. We want to make a really, really good definition about vertical angles so that maybe adjacent angles don't accidentally get classified as being vertical, or complementary angles don't accidentally get classified as being vertical, or vice versa. Does that make sense? Okay. So here's the idea, and I'm going to draw on top of this to kind of walk us through this definition. It says they are vertical angles are two angles such that the sides of one angle are opposite rays to the sides of another. So I'm going to look at this ray right here. Okay? Would you agree that that ray is a side of angle 1? Okay? I'm going to look then at its opposite ray. So its opposite ray would be that ray there. Would you agree with that? Opposite ray being the ray that is traveling in the 100% opposite direction as the first initial ray. Okay? Would you say that ray helps make angle 3?
Yeah.
Okay? So the solid one makes angle 1 or helps make angle 1. The dotted one helps make angle 3. Would you say that this ray also helps build angle 1?
Yes.
Okay? Would this ray be opposite to it?
Yeah.
Does that ray help build angle 3?
Yeah.
Alright, so what we have here is that the rays of angle 1, okay, form angle 1 obviously, but their opposite rays form angle 3. So what we're saying here is angle 1 and angle 3 are vertical angles to one another. Does that make sense to everybody? Now don't think about vertical as being up and down, at least in this situation. Okay? I'm not 100% sure the reason for that terminology, we're using the word vertical here, but it doesn't always mean up and down. Because would you agree that that ray makes angle 2?
Yeah.
Does that one make angle 4?
Yeah. Yeah.
Does that make 2?
Yeah.
Does that make 4?
Yeah.
Are the solid ones opposite the dotted ones?
Yeah.
Okay, so 2 and 4 would also be vertical angles. And they're not on top of one another, right? They're not up and down orientation to one another. So color coding, the blue angles are vertical, the red ones are vertical. Okay? And you can have, no matter what your two lines intersecting look like, you will always have a series of vertical angles. Okay? And in this case we'll always have 2 pairs of vertical angles. Okay? What do you notice though as we work through it? It's not something we're going to talk about a whole lot today, but what do you notice about those measurements?
The midpoint's always the same.
Careful.
They're not the same degree, but it's like.
Okay, so the angles, when we talk about angles, we don't want to talk about midpoints of angles. But you're right, that 71.64 and that 71.64 are the same. I move it there, you get 51.22, 51.22. So what do you think you know about vertical angles? What would be a relationship that we can learn later?
They're like not identical, but the angles are the same.
Okay, the angle, the measurements are the same, they're both angles, so they're congruent angles. Okay? And you're going to see even the angles that I don't have drawn up there. Would you guys agree that this angle here and that angle there are vertical?
Yeah, they have to.
Okay. So, some features that we're going to recognize and use on a consistent basis. It's going to be very important that we can find and identify vertical angles. Okay? They happen all the time inside some of the things that we want to do. For instance, you'll do this a lot. Let's say that I have what are the 2 shapes that you have there?
Triangles.
2 triangles. But what do you now know about that angle there and that angle there of that set of triangles?
They're adjacent.
Not adjacent. They're vertical. Okay? So that's going to tell us something very nice about those 2 triangles later on. Okay? So vertical angles become very useful to us in the long run. Okay? Basically today is just identifying some types of angles, some key features about some of these things, and how we are supposed to interpret and read these things. Complementary. Okay? Whenever we're in math and we use the word complement, it is talking about having an understanding of an entire grouping of things, and then 2 separate ways of breaking that group up. Okay, so let's say that this entire group, this entire class is the whole thing that we want to talk about. But I take these 2 rows, take Charlie and this row, and I send them out in the hallway. Okay, who would be left in the room? Raise your hand if you're left in the room. Okay, so you guys would be considered the complement of these 2 rows. Does that make sense? Okay. If I took the entire class and I cut this row out, I said, you guys go to the hallway. These guys would be left in here, right? These guys would be the complement of this row, okay? So basically, when we talk about complement, we understand the whole amount, okay? We then understand how that can be broken up into groups. And if I say, let's get rid of this group, what is left over? The leftover would be the complement, okay? So whenever you see that word, it's used a lot in math. A lot of times you're going to put a tag word on it. Here we got the word angles. So now we know we're talking about complementary angles. And we're going to use that approach. We're going to use that idea. I'm going to tell you two angles that sum to 90, right? Okay? So that's the total. That's the whole group. But if I tell you one of them is 20, you can tell me the other one's what?
20.
Huh? 70. Okay? One angle is 20. The complement of it is 70. Okay? So it's everything else, right? That gets me to 90. Okay? If I tell you one angle is 30, what's its complement?
70.
60.
I was thinking 100.
If I give you 60, what's its complement?
30.
30. So 60 is 30's complement, but 30 is 60's complement. Does that make sense?
Yep.
Okay. So I have a brother. He's my brother, but I'm his brother too. That's that idea.
Yeah.
Okay. When we look at angles 1 and 2 up here, angle 1 and angle 2, are they complementary?
Yeah.
Yeah, we can use the angle addition postulate to say that 1 plus 2 should equal that total of 90 degrees, right? They're showing me 90 degrees with that little box in it. Do you know what measurement of angle 1 is?
No.
Well, yes. Well, yeah, half a 90.
How do you know it's half a 90?
Because the other side's got to be half a 90.
How do you know that?
Because
It's
they're
going-
both equal 90.
How do you know that?
Because it's got that little square.
Okay, it's got the little square in it. It says they're both going to add up to 90, but how come maybe one of them's 46 degrees, the other one's 44 degrees? Does that still add up to 90?
Yeah.
Yeah.
But no.
Yeah.
Okay,
No,
you see
no.
that square?
Uh-huh.
There, like in there? It's going like halfway through that.
That's what I'm saying, Carter.
You don't know that.
I can see it. Yes,
I
I do.
Yeah, you don't know that.
Okay.
We don't know unless we're being told. Okay? And there's different ways they can tell us whether that's 90 or not, or whether angle 1 is 45 and angle 2 is 45. If they were to tell me that this ray is an angle bisector of the right angle, then yes, that tells us it's 45 and 45. Okay? But we don't know these individual measurements. Alright? We don't want to make assumptions about things. Does that make sense? You get in trouble by doing that, correct? Okay, by making assumptions. And we'll talk more about this later on, but you do not want to make the argument that those are both 45. We talked about it the other day. I drew this picture on the board, right? And I asked you what kind of angle that was.
Yeah.
And some people said 90, right?
Yeah.
And we talked about how maybe it is 90,
Maybe it's a little off.
but maybe it's a little off. Kind of like Carter.
Yeah.
Okay, so it could be like 89.99, right?
Yeah.
Still not 90. We don't want to say it's 90 until we're able to identify and label it as 90. Okay, whether it's been told to us in a definition, whether we're looking at a couple of different theorems and postulates and how they intertwine with one another to prove to us that it is 90. We do not want to make conclusions that are inaccurate. Okay? Now, because you can't say it's not 90, doesn't mean it's not 90. Does that make sense?
Yeah.
So I'm saying we don't know this is a 90 degree angle or if it is a 90 degree angle, but it's not eliminating the possibility that it could be 90 degrees. Is that alright? Just by not saying something doesn't mean that person is, or that thing is not classified that way. For instance, I'm not saying Carter is an A plus student, okay, but that doesn't mean he isn't an A plus student. Does that make sense? Okay. Just keep those things in mind. These two angles are adjacent, right? These two, are they complementary, A and B? Okay. They add up to 90, 47 plus 43. Are they adjacent?
Yeah.
Do they share a vertex?
Oh no, not A
Nope.
and B.
A and B are not adjacent, okay? So what that tells us is that complementary angles, look at those two pictures, complementary angles do not matter whether they're adjacent or non-adjacent. They just have to have the criteria of adding up to 90. Does that make sense? Okay. Now here's a question. Is this picture
Yes.
would we agree that the overall angle here is 90 degrees?
Yeah.
Okay, I'm going to number that angle 1, angle 2, and angle 3. Are those three angles complementary?
Yeah.
No.
Yeah. 'cause
Yeah.
they're all
Okay, you say yes, so tell me why you say yes.
Because they all have to add up to 90.
Okay, so you're saying they add up to 90. You're saying no. Tell me why you say no.
I just want to be opposite part.
Okay. Charlie, you're saying no.
No, yeah.
Okay, you're saying, anybody saying no?
Wait, what was the question again?
No, or what? Well, Spade says no.
Are these three complementary? Why are they not complementary? Okay, the definition says it's two angles
Oh, that's right.
that add up to 90. Okay? A lot of people want to say complementary angles that add up to 90. Supplementary angles that add up to 180. And that's fine, but you're being lazy about it. And being lazy about it can get people to think, well, it doesn't matter how many I have. By definition, complementary and supplementary eventually have to be two angles that add up to 90 or two angles that add up to 180. Does that make sense? And here's the logic between that. If I said we're talking about the class and being complements in the class, right? So if I take these two rows and get them out of the room, we know what the complement is, right? We know you guys are left over, okay? Well, if I say that we've got three groups, okay, and you know, let's just go back to this idea. If I look at this picture here, if I say that I know that this is 25 degrees, can you tell me what angle 1 and angle 3 are individually?
Yeah.
You can tell me how big angle 1 is right now?
No.
No,
Take
you
90
know
minus
that it's less than what?
25.
65 degrees, right?
Yeah.
Okay, because 1 and 3 have to add to 65 to make 90 with the third one.
Divide that by 2.
Well, I don't know that they're directly in half. Okay, they look like they might be equal, but we don't know that. Okay, so you can't specify, you can't narrow down what measure angle 1 is and measure angle 3 is individually. And when we talk about the word complement, we should be able to narrow it down. Okay, I should be able to tell you one part of it, you tell me exactly what the other part is. With those things, you can't do that. Does that make sense to everybody? All right. And you guys have learned supplementary as well, right?
Yes.
Supplementary
Yes.
from previous grades.
Yes.
If I tell you one angle is 50, the other one's 130, so they're adding up to what?
180.
180. And that's two angles. Two angles who sum to 180. Okay? Again, looking down here at these pictures, angle 3 and 4, they're adjacent. If I look at angle B and angle C, they are not adjacent, but adjacency doesn't matter for complementary and supplementary. Okay? It is really nice that when we're working with complementary angles and we're working with supplementary angles, if the angles are adjacent, it makes things really nice and convenient, but they don't have to be. Is that all right?
Yes.
Okay. Let's go down to, I'm going to skip a couple slides, we'll come back to these.
Yes.
But I want to get down to this one. Okay? It says a linear pair. Okay, pair meaning what?
2.
2.
2.
Okay. And linear meaning,
The same.
The same.
no, what's,
Equal.
what's the root word for linear?
Line.
Line.
Line. Okay. So linear pair refers to angles. Okay. So it's two angles that when we put them together, they form a line. Okay. So by definition, there it says a pair of adjacent angles. So we know what adjacent means, right?
Yes.
Okay. Same vertex, common ray, no common interior points. Whose non-common sides. Okay. If I look at these two angles, angle 1 here and angle 2. What is the common side?
2.
Side.
The middle one. D.
Okay, what do you call that? It's this one here, right?
Yeah.
Okay, well D is just a point. I want to name that ray.
Line
DB.
BA.
Okay?
BD, I mean.
DB.
Because it doesn't, we want to call that ray BD.
Yep.
We don't want to go DB because then it's kind of telling us that we're going through AC infinitely past line AC. Does that kind of make sense? So if we named it DB, now if it was a segment, I wouldn't have an issue with that. So we got our line here. What is this up here? D, and this is B. If it was a segment, I don't have an issue with that. Okay. But if it's a ray, and it is a ray in this case, if you name it ray DB means it goes on like that. We don't have this portion down there. Does that make sense? So we got to start at B and go to D. So ray BD. Okay. Ray BD is the common ray, correct?
Yeah. Yeah.
Okay. So the non-common rays would be BC
BA.
and BA, right? Those would be the non-common rays. What shape do those non-common rays form?
A line.
A line.
A line.
And that's what this is saying. A pair of adjacent angles whose non-common sides are opposite rays. Well, opposite rays we talked about last week as being two rays that form a line, right?
Yeah.
Okay. So that's what a linear pair is. A linear pair is always going to look like that picture up there. Doesn't matter,
Yeah.
you know, how big those individual angles are. So I might have something that looks like, okay, those two angles are a linear pair. Those two are a linear pair, linear pair, linear pair, linear pair. Does that kind of make sense?
Those are infinite numbers of linear pair.
Yes. Okay. But they can show up however they want to. Okay. In that regard, and then they can also be, you know, there's some linear pairs down here. If I put that ray below the line, is that doable for everybody? Okay. But with a linear pair, what is that angle right there going to be? What did we talk about? A straight line. What its measurement was last week?
180.
180. Okay.
See.
So we come up with this postulate that becomes one of the most influential postulates that we're talking about all year. Okay? It says if two angles form a linear pair, and you can tell that visually. Okay? You're going to see that by a picture. If they form a linear pair, then they are supplementary. And if they're supplementary, what does supplementary mean? They're going to do what?
Supplement.
What we talk about the definition of supplementary mean? Two angles that
Intersect.
no,
Side by side.
not necessarily.
Equal. Can someone help me out?
What does supplementary mean, guys? Yeah, they sum to 180 degrees. So whenever I see a linear pair, whenever I see a picture like this, okay, whatever I call that angle, whatever I call that angle, I'm going to add them together and set them equal to 180, right? Okay. So here they tell me KPL and JPL. That's the angles we're going to talk about. Okay, drawing a picture here. Look at just the names. We won't even get into the problem yet. KPL and JPL. What letters do they share?
K,
P
J.
and L.
P and L. Okay. So P has to be there, and L has to be somewhere on that ray. Because then when I put K there, do I have KPL?
Yeah.
And when I put J here, do I have JPL?
Yeah.
So I got two angles that now have formed a line, right? The
Yeah.
line we formed is that line right there. And yes, we're getting that total to be 180.
Yes.
Okay? Now, does it tell me that K had to be to the left of P?
No.
No. So K and J could actually flip spots if we wanted them to. Okay? And at the end, it might make sense for K and J to flip spots. But they're telling us algebraically that KPL is 2x plus 24, right?
Yes.
JPL, 4x plus 36. All right? Does that look eerily similar to the angle addition postulate?
Yeah, I get it.
Could you like simplify it before you like add it up? Take 2 out of the 2x plus 24, and then take 4 out of the 4x plus 36, and then add it up?
Yeah, but the 2's and the 4 that you do that with can't disappear.
Oh.
So you could write it as 2 parenthesis x plus 12, and then 4 parenthesis x plus 9, but it's not going to make anything easier. It's easier this way. What are those two angles going to add up to?
180.
Because by knowing a linear pair, and then linear pairs are supplementary, and then working back to the last slide, supplementary meant to add up to 180, we now know we can take 2x plus 24 plus 4x plus 36 is equal to 180. And if you remember what I talked to you about early on in this course, we should always be able to say why something is the way it is, why something's true. I know that equation is true now because I know that those two angles form a linear pair, okay? Because they form that line, right? I've got two non-common sides of two angles forming a straight line, okay? So that they're supplementary. And then I can work back and say, well, supplementary means they add up to 180. And that proves to me why that equation is true. Is that doable?
Yeah.
So now I can go ahead and solve that, right?
Yeah.
So 6x plus 60 equals 180.
Yeah. Minus 60 is 120.
And then
Divided by
6.
6 is 2.
20.
20.
So now if that's 20, I come back up here, this angle becomes 64 degrees, and this becomes 116, right?
Switch it around.
Okay, so it doesn't look like that should be right, correct?
No.
It looks like I got the angles mixed up. Okay, 64 looks like it should be 116, 116 looks like it should be 64, right?
Yeah, we're trying.
But remember, I never knew where P to L was. Maybe P to L should have been over here, right? Or maybe I didn't know where K and J should have been, so they could be flipped, okay? The reason we drew the picture is so we can organize our thoughts and create the equation. The equation then leads us to x equals 20, so we want to believe the math and not so much believe the picture. Does that make sense?
Yeah.
Alright, now if you wanted to make when you're done, you want to make your picture look more accurate, that's fine. We'll put K there and J over there, that fixes things, okay? But I would prefer you to draw a picture to organize your thought and then rely on your math and your calculations to justify what you've done, okay? The next one, what does bisect mean?
They, like, 2 lines.
Isn't it something that separates a segment?
Okay, so we've talked about segment bisectors, right? And it separated a segment into 2 equal parts, correct? Well, that was called a segment bisector. Now we have an angle bisector. So what do you think we're separating here?
Angles.
An angle into how many parts?
2.
2, and what do you think you're going to know about those 2 parts?
They're
They're gonna equal
They're
1
gonna
angle.
equal 1 angle.
Nope.
They're the same.
They're the same.
Oh.
When you bisect something, you are creating 2 smaller yet equal parts. Okay? So I'm bisecting that angle FGI up there. Okay?
See.
So if I bisect, so let's say GH is a angle bisector. Okay? So it's taking this larger angle, it's cutting it into 2 equal parts. Well, those 2 parts are labeled as 3x minus 3 and 4x minus 14. If an angle bisector takes an angle and cuts into 2 congruent angles, what can I say about those 2 measurements? What's the relation between this measurement here, whatever it may be, maybe it's 20 degrees. What would this one be? 20 degrees, right? Now I don't know exactly what they are, but if this one's 3x minus 3, how does that relate to 4x minus 14? They should be what to one another?
Equal.
They should be equal. And now you've got a relationship that you can solve that equation with. Solve for x, you can then find what those individual angle measurements were. Does that kind of make sense?
Yeah.
All right. Angle bisectors do the exact same thing for us that midpoints do for segments. But angle bisectors do it for angles. Okay? Make sure that we do the math Excel assignment tonight. Okay? We'll talk about any questions that you might have on that tomorrow.